Hello, I'm Sherry Dunbar, the Senior Director of Scientific Affairs Programs for LumenX and DiaSorin. And over the next few minutes, I'm going to tell you how the best multiplexing technology got even better, xMAP INTELLIFLEX. To begin, let's take a walk through the xMAP instrument timeline. When the company was founded in 1995, we had some beads and a software, but you would have to run your multiplexed assays on a flow cytometer. So we quickly realized that it would probably be better if we could come out with a flow analyzer that was specifically designed and optimized for reading xMAP microspheres. And in 1999, we launched the LumenX 100, which was our first flow analyzer for xMAP technology. The LumenX 100 was 1/5 the size of a flow cytometer, 1/5 the price, and 5 times faster. A few years later, in 2005, we came out with the LumenX 200, which was an upgrade to the LumenX 100. We made several hardware changes and improvements based on feedback from customers. In 2009, we came out with the FlexMap 3D, which was our first high throughput system. This system was not only capable of running both 96 well and 384 well plates, but it could also multiplex up to 500 different microsphere sets. In 2010, we launched the MagPix. The MagPix was really intended to meet the needs of the other end of the spectrum, labs that needed a smaller instrument to take up less bench space and also could do a 50-plex or fewer. And you can see that there was quite a gap in here until in 2021, we launched the newest xMAP system, the xMAP INTELLIFLEX, which is what we're going to learn about today. So first, let's talk a little bit about the features of the current flow analyzers prior to the launch of INTELLIFLEX. So the LumenX 200 is flow-based. It reads up to 100 bead regions per well, and it can analyze a full 96 well plate in about 45 minutes. This means that it can run up to 12,800 tests per hour. The FlexMap 3D is also flow-based, but it can read up to 500 different bead regions per well. And because of its dual sample fluidics paths, it can analyze a 96 well plate in just 20 minutes. And a 384 well plate can be read in 75 minutes. This means that you can run up to 144,000 tests per hour in the 96 well format, or up to 153,600 tests per hour in the 384 well format. So this is a more than 10-fold increase in the tests per hour compared to the LumenX 200. So now let's talk about the xMAP INTELLIFLEX. This is the same versatile multiplexing platform that you trust and that you've come to know and love, but it has enhanced features and an overall improved user experience. The multiplexing capacity is also 500 beads per well, just like the FlexMap 3D, but there's been an increase in the dynamic range. Now in the Reporter 1 channel, you can achieve up to 5.5 logs. That compares to 4.5 logs in FlexMap 3D. It runs both 96 well and 384 well plates, but the PC and the monitor are integrated into the instrument, so it has a smaller footprint than the other instruments. The read time is the same as FlexMap 3D, with a 96 well plate read in 20 minutes and a 384 well plate in 75 minutes. The system design is modular and the laser mounts are fixed. And it also has a wide, clear sliding door in the front for probe access. So this is going to make probe height adjustment much easier. And then in the bottom right-hand corner, you can see the INTELLIFLEX DRSE model, which stands for Dual Reporter Side Eject. So this model has all the features we just described for the standard INTELLIFLEX instrument, but it also has a dual reporter configuration. We added an additional laser to provide 2 reporter channels. And the second reporter channel, RP2, has a 4.5 log dynamic range. And then you can see here the side eject microplate carrier allows a convenient connection to existing laboratory automation equipment. So let's look at the internal workings of the xMAP INTELLIFLEX. So you can see here that the footprint is much reduced compared to both the LumenX 200 and FlexMap 3D. This is because of the integrated PC and touch screen. But you can also connect a keyboard and a mouse to the instrument if you prefer to run the software that way. You can see that there are multiple modules inside, one containing the optics, then there's a fluidics module and a plate module. And so having this modular design really allows easy access for repairs or maintenance. And so field service can get in there and work on the components very easily. The xMAP INTELLIFLEX is also what we call backward compatible. And what this means is that any xMAP assay that you're running today will run exactly the same and be compatible with the new INTELLIFLEX instrument. Let's take a closer look at the optics. So on the left side, we have the standard single reporter xMAP INTELLIFLEX. And the layout is really the same as what you know from the FlexMap 3D. We have two lasers, a red laser and a green laser. The red laser excites the internal dyes in the microspheres and sends them over to our avalanche photodiodes, or APDs, for classification. Then we also have the DD, or doublet discriminator, that differentiates single bead events from anything that is not a bead or is smaller or larger than a single bead. The green laser excites the reporter fluorescence and sends it over to a photomultiplier tube, or PMT. In addition, there's an extended dynamic range, or EDR detector, that takes some of that signal and is able to analyze it past the point of PMT saturation. And this is what gives you the 4.5 or 5.5 logs. On the right, we have the DRSE model, where we've added an additional violet laser to provide the second reporter channel. So in this case, the green and the violet lasers are exciting the surface-bound reporter fluorescence and sending it to either the first PMT for the RP1 channel or a second PMT for RP2. Let's talk about some of the other enhanced features. xMAP INTELLIFLEX has networking and electronic records compliance. It's a modern, secure software that meets the cybersecurity and performance needs of a modern laboratory. It's easily integrated into existing domain infrastructure to manage user access through centralized IT departments, so you don't need additional passwords. And then there's rich integration support. There's robust documentation and also dedicated to support to quickly and easily add your INTELLIFLEX to your network. It's also 21 CFR Part 11 and Annex 11 compliant, with audit trails, electronic signatures, digital signatures, data integrity, secure login, and backup and archive. And then there's also documentation to explain and describe each of these features in much more detail. We're also showing down here in the bottom right a screenshot of a plate-specific audit trail using the xMAP INTELLIFLEX XLS report. So now let's talk a little bit about software. Our current INTELLIFLEX software is version 2.0, and some additional features that have been included is the ability to reanalyze plates. So now you can easily edit the parameters from previously acquired plates and then replay them. This is known as replay batch and exponent. So say you want to change your gate settings, maybe make your gate a little more narrower, you can do that and then reacquire the data from that previously run plate. Backup and restore. So now you can safeguard against data loss with a new in the graphical user interface backup functionality. The side eject. In DRSE models only, this allows you to seamlessly interface with automation hardware, which makes the workflow more efficient and productive. The automation module, which is optional, increases productivity and reduces manual effort by connecting to automation hardware using the modern REST application programming interface. And it has electronic records compliance module, which is also optional. And this allows you to stay compliant with electronic records regulations with easy-to-use traceability features. And now coming soon is our next software, version 2.1. Some of the new features that are going to be included in this version of software is an optimized bead map. So the bead map is being optimized to improve bead performance across all of the xMAP instruments. And this is going to help reduce calibration and verification failures. There's also new features for lot management. So now you can remove expired or out of stock lots from your list. And this is going to help you reduce errors by making it easier to select the correct lot. Maintenance countdown timers. This provides users with a status of maintenance operations. You always want to know how much time you have left during a maintenance routine, especially something like a alcohol flush that takes 5 minutes. If I know I have a few more minutes, then that gives me time to go grab some other stuff that I need to set up the next steps of my experiment. There's also improved maintenance. Specifically, it's easy to manually calibrate the probe height for 384 well filter plates with fewer clicks. And it's user upgradable. So now moving forward, you'll be able to obtain the latest software sooner by eliminating the need for a field service engineer to come out for a visit. So if you're on version 2.0 software, now you'll be able moving forward to self-install any additional upgrades. So now that we've talked about the hardware and software features, let's talk a little bit about performance. This data was provided to us by our partner at Thermo Fisher Scientific, and it's showing the performance of their cytokine chemokine growth factor 45-plex procardiaplex panel for the INTELLIFLEX compared to all of the other instruments and settings that are available. So what we're showing here on the left is just the standard curves for the ILA analyte. And so what you can see is whether you ran it on a Luminex 200, which would be in the blue line, or the Luminex 200 mode in INTELLIFLEX, you're getting the same results with the red line just laying right on top of the blue line. Likewise, for FlexMap 3D, whether you run the assay on the FlexMap 3D, which is in green, or you run it in FlexMap 3D mode on the INTELLIFLEX, you're getting exactly the same results. So this is what we mean about backward compatibility. The INTELLIFLEX has multiple operating modes. So if you want to see your data the way that you're used to seeing it on the Luminex 200 or the FlexMap 3D, you are able to select that operating mode to run your assays on the xMAP INTELLIFLEX instrument. And on the right, you can see where some samples have been run and whether you're running Luminex 200 or Luminex 200 mode, FlexMap 3D or FlexMap 3D mode, all of those points are aligning up right on top of each other exactly where they should be. So now let's talk about applications. So let's start with something simple, a single reporter example. Here we're describing a serological assay where you have specific antigen coupled to each of your bead sets, and you want to measure the antibodies in the sample to those antigens. And so in the reaction, all of the antibodies are binding, whether it's IgG or another isotype, IgA, IgM, it's all binding. But in a single reporter instrument, you can only detect one at a time. So here we're showing that in well 1, we're measuring IgG by using an anti-IgG detection antibody labeled with PE or phycoerythrin. But now if we want to also measure, say, the IgA response, we have to set up the same reaction in a second well with a different detection antibody. And so here in well 2, we have the detection antibody for IgA also labeled with PE. But now, if we have the dual reporter instrument, we can do all of that in a single well. So here we're showing as the bead gets classified by the red laser, and then it gets excited by both the green laser for reporter 1 and now the violet laser for reporter 2. So in the reaction, all of the antibodies are binding, but we have 2 detection antibodies, each labeled with a different dye that's compatible with each of the 2 reporter channels. So for IgG, we're showing a PE labeled detection antibody. And then for IgA, we have a detection antibody labeled with a blue dye that fits into the reporter 2 channel. So now let's look at some real data using an assay similar to this one described in this cartoon. So here we used our xMAP SARS-CoV-2 multi-antigen IgG assay kit, but we swapped out some different detection antibodies to look at different isotypes in different reporters. So what we have here is 3 panels, identical reactions, all run in dual reporter mode on the instrument, but we either had just one of the detection antibodies or the other detection antibody or both together in the same reaction. So on the left, panel A, you can see that when we have an IgG PE labeled detection antibody, we're seeing a dose response to the IgG signal in the red line. And the signal in the second reporter channel is negligible. It's at background levels. In panel B, we're using an anti-IgM detection antibody labeled with super bright. And you can see a nice rise in signal as you use a lower dilution for the serum. And then in the RP1 channel, the signals are at background levels. It looks at the 1-to-1 1 to 400 dilution, that there is a little bit of an increase in signal. However, this is on a log scale, so it really is at background levels. But more importantly, in panel C, you can see that when we ran this in dual reporter mode with both detection antibodies present, the signals that we're seeing in the solid lines are identical to what we saw when we only had one or the other detection antibody present in the dotted lines. So this proved that there's no cross-reactivity or interference between the two reporter channels. Of course, we wouldn't expect to see that since they are at different wavelengths and both for excitation and emission. However, we needed to prove that, and so that was proven here by these experiments. So now we wanted to look further and look at some different samples to see what we were able to measure with the dual reporter assay. So here we looked at the dual reporter assay compared with single reporter xMAP readout. And so on the far left, we're measuring immunoglobulin to the receptor binding domain of SARS-CoV-2, showing MFI. And we're looking at this over time after vaccination. And so you can see that when we measured IgG using a PE-labeled antibody and simultaneously measured IgA using a brilliant violet 421 antibody, we see a sharp increase in signal antibody titer after about a week or so after the vaccination. And then it levels off and remains pretty high. And then when we boost at 21 days, we get another spike in increase in antibody titers. And then the IgG remains pretty constant throughout the 45 days of the measurement, and the IgA is starting to drop off more rapidly. In the center, we used the assay with the dual reporter signal to look at the differentiation of different patient types during the COVID era. And so what we have is samples from before COVID in blue, and then we have patients that had never had COVID, but were vaccinated with an RBD containing vaccine. And then in red, we have previously infected individuals. So what we're showing here is the MFI signal against the receptor binding domain detected with a detection antibody for IgG. And then on the y-axis, we're showing detection of signal of IgG against the nucleocapsid. And so you can see in the pre-COVID era, the samples are all reading at background levels because there are no antibodies, no one's been exposed yet. In black, you can see that when people were vaccinated but did not have COVID, they have a high signal to the RBD, which was what was contained in the vaccines, but no signal to the nucleocapsid because they've never been infected. And then in red, you can see patients that were previously infected, and they're showing high signals to both the RBD and the N antigen. On the far right, we're comparing the signal for IgA using a brilliant violet 421 labeled antibody in INTELLIFLEX in the dual reporter mode compared to the IgA signal using PE in the other xMAP instruments, MagPix in red, Luminex 200 in blue, and FlexMap 3D in black. And you can see that these curves are laying right on top of each other with slopes approaching 1. R squared values are at 0.98 to 0.99. So very consistent performance for both reporter channels on the INTELLIFLEX instrument as compared to the single reporter instruments. So now that we understand how to use dual reporter in this example, let's think about other things we might be able to do with it. When I think of dual reporter, one of the first things that I think about is looking at post-translational modification, specifically phosphorylation. You have one target on the bead, but you're able to use different reporter antibodies to measure different parameters of that target that's on the bead. So for example, we can have a detection antibody for total or unmodified target, and we can have at the same time a detection antibody to measure the amount that has been phosphorylated or modified. We can also look at protein-protein interactions with different target reporter antibody or reporter molecule labeled probes. We can look at antibody isotyping, as we've just seen, looking at IgM and IgG at the same time, looking at class switch between IgG1, IgG3, for example. And also, if you were to do this in a competitive format, you can also measure the neutralizing potential of the antibodies that you're detecting. We can also look at free versus bound drug if we have detection reagents that can simultaneously detect the two different forms, and then also things like bispecific antibodies and fusion proteins. So while we can think about these different applications, we're already starting to see some publications in the literature where people are using INTELLIFLEX and then telling the readership about it. So let's move now to xMAP in the literature. Our first publication came from University of Rochester, and this group developed a 3-plex assay to measure antibodies to SARS-CoV-2 spike, RBD, and nucleocapsid antigens multiplexed in a single assay on xMAP INTELLIFLEX DRSE. They had previously developed this assay on the FlexMap 3D instrument, but they needed to measure IgM and IgG in two separate wells, having just a single reporter. So in this study, they were able to convert the assay to a dual reporter assay and measure both antibody isotypes simultaneously in the INTELLIFLEX DRSE model. And so on the bottom left, we're looking at the dose response of antibodies from days from symptom onset in COVID patients for S in blue, RBD in red, and N in green. And you can see for IgG, a nice response fairly shortly after symptom onset, and then the antibody remains relatively steady as it drops off, but then it remains steady out to several months after infection. IgM has a spike, an increase in signal early on, but then it levels off much more quickly. And then you can see for the N antigen, the IgM response was not as strong in these samples that were tested. In the upper right, they measured the performance of using IgM and IgG to classify controls versus cases. And so here they're showing the area under the curve, looking at S, RBD, and N, and as a function of days from symptom onset. And so you can see pretty good performance even with IgM using the S and RBD antigens to determine that with areas under the curve of 0.9 or greater. N was not quite as strong with area under the curve, maybe approaching 0.9 after about a month from symptom onset, but then it dropped up much more quickly. You can see on the right, looking at IgG, that was a much stronger indicator to be able to classify cases versus controls, with pretty much from the beginning of symptom onset out to a month and a half, nearly perfect area under the curve, 0.9 or greater. In the bottom panel, what we're looking at here is where they took the assay and converted it to a competitive immunoassay format and used ACE2 as a competitor to measure neutralizing potential of the antibodies that were generated in patients in various days from symptom onset. So on the left, we have the results for IgM, and what we're showing is the percent of residual signal after incubation of the samples with ACE2 prior to adding it to the multiplexed bead assay. And you can see that we've got pretty good inhibition with the S antibodies, with about 50 to 60% of the signal remaining, so pretty good inhibition. For the RBD, it was not as strong, and of course, we have no response to N because ACE would not inhibit antibodies that were raised to the N antigen. So it's actually kind of a nice control for this assay. You can see on the right, looking at IgG, you got much stronger inhibition, and so a much higher indication of neutralizing potential of the antibodies that were raised in patients after symptom onset. So with at least a 50% inhibition for both the S and the RBD. And again, no impact on the N. So this study, in addition to being published here in Microbiology Spectrum, they also published the experimental method, which can be found at the Journal of Visualized Experiments, along with an accompanying video showing exactly how to perform the experiment. Next, we have another serological assay, also for SARS-CoV-2, but this one comes out of Rush University Medical Center. And what this group did was they developed a 3-plex assay looking at spike, membrane, and nucleocapsid antigens in a dual reporter mode to be able to measure two antibody isotypes at the same time. They wanted to be able to measure all IgA, IgM, and IgG, but understanding that you can only do two at a time with the INTELLIFLEX DRSE model. However, that's still decreasing your number of reactions by a third. And so the first thing that they had to do was develop and optimize the assay. And so on the left, they're looking at which antibody, isotype detection antibody and dye pairs were the most compatible. And so in panel A through B, and C, in the first column, they're looking at using an anti-IgM labeled with super bright for detection of each of these different antigen antibodies. And then in D, E, and F, the second column, they're looking at using phycoerythrin to measure IgG. And then in the far right column, G, H, and I, they're using also a PE-labeled antibody to measure IgA. And so what they show here in these panels is, again, whether they had one reporter or both reporters present, there was no difference in the performance and no interference between either the anti-isotype antibodies or the different reporter dyes. So now that they had developed and optimized the assay, they took a selection of patient samples to test in combination IgG with IgM or IgA with IgM in the dual reporter mode. And you can see here that shortly after vaccination, you can measure seroconversion looking at antibodies to spike, IgA, IgG, and IgM. And you can see a pretty good response fairly shortly after the vaccination, and then the antibodies are maintained for a period of time, and then they start to drop off. You can also see that different patients had different responses and that the IgA dropped off more quickly. So they found that this dual reporter assay could be very useful for monitoring seroconversion in vaccine subjects. Now we have a different application also using the dual reporter. And here we have a dual reporter blockade assay to evaluate B-cell epitope peptide vaccines to elicit anti-tumor immunity. This study was done by a group at Ohio State University, and this work was done first in mice before moving on now to human clinical trials for these peptide vaccines. So they started, as shown here in the figure, a biotinylated PD-L1 antigen, which they pre-incubated with anti-PD-L1 antibodies, either control or subject serum. Then they added this complex to PD-1 conjugated beads to capture the available PD-L1 complexes. They added streptavidin phycoerythrin to measure the bound PD-L1, and then they used a brilliant violet labeled anti-species detection antibody to measure the anti-PD-L1 antibody. And the figure in the top right is showing the percent of binding inhibition over increasing antibody concentrations. So this is the blockade assay. And you can see that the control is showing the highest inhibition at the lowest concentrations. But several of these peptide vaccines also showed strong inhibition at over the course of the different concentrations, with the one in green, the anti-PD-L1 50, showing a pretty high response with inhibition approaching 80%. And then in the bottom, we're looking at the measuring of the binding efficiency of the anti-PD-L1 antibodies to the PD-1. And so this, in addition to this publication, they also published the method, so the experimental protocol for this assay, in the Journal of Visualized Experiments, along with an accompanying video that is either out now or out soon. So what they found was the bead-based dual reporter blockade assay verified results they had seen in ELISA, and it helped them better investigate the blockade of the PD-1-PD-L1 interaction in a fluid phase, because this eliminates potential steric hindrance that you might find if you're binding epitope availability issues associated with immobilizing recombinant proteins on the bottoms of the wells. So here they've pretty much eliminated any problems or variables that would be associated with the antigen being attached to a solid support by having it in solution. And so the microsphere analysis was directly correlated to the ELISA blocking results using this reverse blockade assay. Next, we have another serological application, but looking at antibodies to Epstein-Barr virus. The group at the German Cancer Research Center developed a dual reporter serological multiplex assay to look at detection of IgA and IgG antibodies to Epstein-Barr virus in nasopharyngeal carcinoma patients. Previous studies using this assay were performed on the single reporter Luminex 200 system. Epstein-Barr virus antigen-specific IgG and IgA had to be measured in separate wells using PE-labeled anti-species detection antibodies. And since they were running this in 2 wells, they went ahead and did different dilutions of the serum depending on whether they were measuring IgG or IgA. Since IgG is typically high, they used a 1 to 10,000 serum dilution for that reaction. But for IgA, which is lower, they used a 1 to 100. So the first thing that they had to do to convert this into a single well dual reporter assay was to determine a serum dilution that was suitable to measure both isotypes. So through experimentation, they determined that using a 1 to 1,000 dilution allowed both to be measured quantitatively. So on the left, they're comparing the results of a 1 to 10,000 dilution on the Luminex 200 with a 1 to 1,000 dilution on the INTELLIFLEX, and they got pretty good correlation here. In the center, they compared a 1 to 100 dilution to measure IgA using PE on the Luminex 200 versus a 1 to 1,000 dilution using Brilliant Violet 421 on the INTELLIFLEX. The lower signals are obviously due to different dilutions and also different reporter dyes and different reporter channels, but they still found it to be measurable. And on the right, they compared 2 second reporter dyes, Brilliant Violet 421 with Super Bright 436, and they saw no difference. So after they optimized the dye selection and secondary antibody dilution using PE for IgG and Brilliant Violet for IgA, they found that a 1 to 800 dilution was good for measuring the IgG with PE, and then a 1 to 1,000 dilution for measuring the IgA using Brilliant Violet. So they did those detection antibody dilutions and combined them together in the dual reporter assay. And so then they found that there was no cross-reactivity again between either the dyes or the different reporter channels. So in summary, they successfully developed a dual reporter serological multiplex assay to simultaneously detect IgA and IgG antibodies in the serum of NPC patients. And also additional data in this publication shows that how they compared banked samples that were previously measured on the Luminex 200 with the results now measured several years later using the dual reporter assay. And the results were very correlated very, very well. So they found that this assay could be a promising tool to conserve serum samples when evaluating IgA and IgG in seroepidemiological studies and provides a cost-optimized method for NPC screening within endemic areas. Finally, I want to talk about this next example, also a dual reporter serological assay, but this time for Lyme borreliosis. And since earlier at our xMAP Connect Symposium, we had a talk about this study as well as a poster. I'm not going to describe it in too much detail because you need to take a look at those talks and those posters. But this study was done by the NMI, and it was published in BMC Infectious Diseases. And what they describe here is a Borrelia multiplex, a bead-based multiplex assay for simultaneous detection of Borrelia-specific IgG and IgM class antibodies. So they developed a multiplex serological assay using a variety of antigens from different Borrelia species that cause Lyme borreliosis. And then they ran it as a dual reporter assay on the INTELLIFLEX to simultaneously monitor specific IgM and IgG responses over the course of the disease progression. The dual reporter assay, they found, retained the analytical performance of the single reporter 2-well version that they ran on the FlexMap 3D, but allows them to acquire double the data in less time using fewer resources and a reduced sample size requirement. They found high intra and inter-assay reproducibility and good parallelism of the dose responses between the results on the INTELLIFLEX and the FlexMap 3D instrument across the entire dilution range of serum that was evaluated. They also went a step further and automated the assay steps using liquid handlers and then ran the assay in both the 96-well and the 3D-well format on the xMAP INTELLIFLEX. In addition to this, they also published their method at the Journal of Visualized Experiments, which you can see from the citation here in gray at the bottom. And it'll also have an accompanying video so you can see exactly how to perform this experiment. And with that, I come to the end of my presentation, and I hope that you agree that I have shown you how the best multiplexing technology just got even better with the xMAP INTELLIFLEX. Thank you.